Hello, everyone. Good morning, good afternoon. My name is Tiago, and I've been working with computers since kind of like forever, I guess. Pretty much like most of you, we've been working with text since forever, okay? At least since our times as kids. And nowadays I do product management, development consulting, and I train people on Python. And throughout my professional career, I always found that people with a technical background, be it programmers, developers, analysts, didn't fully grasp the fundamentals of texts and computers in the way things really work behind the scenes and how those things depend on the historical evolution, not only of languages, but also, of course, of technology and computers. Say this clicker works, and it does. Like many of you, Mary has registered for a best customer care session somewhere, and she got a confirmation email. It goes like, "Dear Mary, thank you. We're really happy to have you in our session." It turns out that Mary has a friend. She's called Amélie, and she's French. She also registered for this event, and she got an email like this. "Dear Amélie, thank you for this. This is great customer care, isn't it?" It should have been Amélie. Now, you don't want to be on Amélie's shoes, and you certainly don't want to be the one who's sending emails to your clients or your customers like this. Some of you, many people in at least the Python analytics communities, have experiences like this. They try to bring in some tabular data from a CSV file, and they get the dreadful Unicode decode error, blah, blah, blah. And they don't really grasp it, and they don't really understand what's going on here. They know there's some kind of thing that they can add to the code that somehow fixes it, and yeah, we've got competition. Great, thank you. They don't really understand how to fix this. They know they can use something. They make the problem go away, but they don't really understand what's going on, okay? This is not strictly Python, and maybe something most of you don't know, and maybe it's the key takeaway that you can take home or to your work and fix your code, okay? Modern languages have great support for multi-language or multicultural strings. And you may have at some point two text strings that look exactly the same, but they compare differently, okay? This is important. And by the way, even though modern technologies handle text processing pretty nicely, okay, and they uppercase resume, and the accented text comes up, okay, and the Strasse German word, it's written like that in lowercase, properly uppercases to a double capital S, which is great. But if you're working with, for example, Turkish text, okay, notice these dotless I's, and you uppercase it, you get this, but you're entering dangerous terrain, okay? To understand why and how things are the way they are, okay, I suggest we start with a journey and the brief history of text, of written text. So let's go back 5,000 years. And here's text. These text writing systems showed up and were created by humans around the globe throughout time without influence from one another. And as time progressed, near our region of the globe in the Mediterranean Sea, the Phoenician alphabet and writing system showed up. It influenced in turn the Old Latin, and while at the same time, somewhere else in the world, in Mesoamerica, the Mayan civilization created completely different writing systems. Keep in mind, these things some influence others in a non-systematic approach, okay? Written text is pretty much very chaotic, as anything that has evolved through wars, trade, culture, art, okay? It's about humans, okay? It's non-systematic. There are languages where a given letter or symbol, okay, while it's the same letter, You draw it in a particular way if it's in the middle of the word, but if it's the last letter of the word, you draw it differently, just because, okay? That's written text for you. An example of the Phoenician alphabet and the Phoenician writing system, it led to the Greek and Latin and Aramaic alphabets and writing systems, and which in turn led to these, and Aramaic led to these, and some of these, okay, are pretty modern and used nowadays. We here in Western Europe mostly use the Latin writing system and alphabet, okay? In Greece they use this, God knows why, and the Hebrew community, Arabic communities, these are all modern alphabets and writing systems. And you know what? The Phoenician writing system was written from the right to the left, okay? From the right to the left. But some Greek person decided, we're not going to go right to left. We're going to go left to right because that's the clever way. And that's why Greek, Latin, Cyrillic, and most of us write from the left to the right because someone in Greece decided, no, we're going to go the other way. While Aramaic, Hebrew, Arabic, they're still written today from the right to the left, okay? And by the way, the Phoenician alphabet, which is somehow very similar to ours, where individual symbols and letters represent sounds, they didn't have symbols for vowel sounds. They only had symbols for consonants. And guess what? Modern Hebrew and modern Arabic don't have symbols, letters, let's call them, for vowels as well. Okay, so this all comes together. And it turns out, if you look at it from a scholar standpoint, written text is pretty complex. Why? Because it's created in a non-systematic way by humans throughout the years and centuries. That's a fact. However, written text supports communication, and that's very powerful, written text. So let's go over a brief history of communication, shall we? Now, communication based on writing, okay, as far as we know, started with the Roman Empire with the cursus publicus. How did it work? Someone picked up a piece of paper, wrote a message, gave it to a horse rider, sent the message, and the message is delivered. Pretty simple, okay? And one thing I learned preparing this talk, at least for the fun fact category and for the Portuguese among the audience like me, is that one of the first public postal services in the world was Correio Público, nowadays CTT, okay? It's no longer public, but that's a whole different conversation. It was created in the 16th century, and guess what? It pretty much mimicked the Roman approach at written communication, and we had horse riders and ships. That was it. Kind of slow, but it worked. Move forward in time, and then the telegraph in the 19th century, created by people, Mr. Samuel Morse and people, okay, without disregard for all of those other inventors. So the telegraph was based on electrical wires spanning a somewhat long distance, and it kind of pushed written text in near real time, but it needed skilled operators on both ends of those wires to send the text in what is currently known, and since then, the Morse code, okay? And you could send messages in tens of words per minute, and that was a huge benefit as compared to what we had before. Great. Now, the telegraph required skilled workers, and Mr. Baudot, a French gentleman, decided, well, this is all fine and dandy, but it's too complex. I need to improve on this. And he created this machine, which if you look at it, it looks kind of a toy piano or something. There were 5 keys, and the idea was that you would punch them in combinations like chords in a piano, and different combinations would represent different letters of the alphabet. So he figured that would be simpler than having maybe an operator just pushing a button and pushing dots and dashes like D, 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 D. Was it better? I'm not really sure. But this led to the creation of the first, let's say, kind of binary code for text, which on the other end, it came out on a strip of paper with holes punched corresponding to the positions of the keys that were down at any given moment. This was all serial communication, pretty much like the serial communication we have today in a pair of wires. And it actually represented the first international telegraph alphabet, an international standard predating the modern coding standards that we have today. Well, Mr. Donald Murray, he was a journalist, I think, from New Zealand, picked up on this funny machine from Mr. Bodo and he said, nah, this is still too difficult. We must do it better. So what he did, he picked up on that machine, he picked up on typewriters that were being invented back then in the beginning of the 20th century, those mechanical things that many of you may know what they are, and he created a different code, and now you had a machine with a physical keyboard, pretty much like our current laptops have, where you push a key, out goes through the wire, and on the other end, the same kind of paper strip with punched holes would print, so to speak, the message. And a kind of trained operator could look at the strip and say, this is, I love you, my dear friend, have a Merry Christmas, okay? And that would be the message, for example. Now, in the beginning of the 20th century, there was lots of commercial movement around this type of communication. And the Morcom company was producing machines like these, and the Kleinschmidt blah, blah, blah company were producing machines like this, and at some point they decided, we're fighting together, let's just merge our operations, okay? And one of these companies, I can't really recall which, called their products, their machines, teletypes. And so when they merged the two companies, they called it the Teletype Corporation, and they just branded their products as Model 15, Model 16, and so on. And those of you with a Unix background may be familiar with the teletype name or the TTY or the pseudo TTY. That's all software-based emulation on current Unix systems, your cell phones, my laptop, everything, of these machines from the beginning of the 20th century. They look like this, okay? There's a kind of a keyboard there. Here's a different one. There's a paper, a normal typewriter-like paper, and it looked like this, okay? So it was pretty efficient. Now, at some point in the 50s, computers came to be. And, you know, computers really like zeros and ones, and people still want text. So we need to find a way to encode text as those zeros and ones. And thus, who could have told that I would be speaking about ASCII in the, well into the 21st century? Well, here I am. Well, ASCII is an incredible thing when you go and study it, how it came to be. But it's essentially a compromise between the needs of early computers and of these teletype-like machines, because these machines were pretty dumb, pretty electromechanical, okay? The fact that they became the first text-based terminals in the Unix systems is just let's say, an accident of history, because these were kind of separate worlds. So what's the ASCII table, okay? The ASCII code maps a 7-bit number into, let's call it a character, a symbol. Okay, this is a possible representation. We have the 3 most significant bits on the left and the 4 least significant bits here. And let's go on a quick tour and see why this is a combination of a teletype and a computer. Well, these funky things that most of you know that are control codes, these were useful for teletypes. For example, we still use them today. The carriage return that brings the cursor on our terminals back to the first column. On these machines, it pushed the carriage, the printing carriage, to the left. Or the line feed, pushing the paper one line up, okay? Or the EOT, okay, that's the byte 4, or Control D. Back then, on those systems, you typed a message. You needed to signal the other end that I'm done. This is the message. You didn't do that with the final period, okay? You did that with a meta character that was EOT, end of transmission, which is still signaling end of file on modern Unix systems. You just type Control D on your shell, on your Unix shell, and away it goes, okay? Now, this mapping here is useful for computers because the digit representation matches the lower nibble value of that byte. So that helps computers translate input into a computable number that can be used for processing and then converting it back into display for a human. And if you look at this mapping here, why are these aligned like this? Well, this is a subset of the keyboard of one of those teletype machines back then. And if you look, there's a perfect match between this vertical relationship and what was on these keys. Why is this made this way? If you note, there's a single bit of difference. That's the third bit there from the left between the top row and the bottom row. So these machines, okay, when you just hit or held down the shift key, they not only move the carriage such that a different character would be printed locally, but they would also either toggle on or off an electrical circuit while the shift key was down, such that that bit would be on or off. So that's very simple mechanical decisions, okay, that lead to what we have today. These things are still true today. By the way, this is the look of the full keyboard, and I have links to all of this if you want to explore later. What about the letters, okay? Okay, these are the letters for the Latin alphabet. Why are they laid out like this? Again, if you notice, the difference between the upper and lower case ranges of letters is a single bit. So it's simple for a computer. And think 1950s, 1960s computers. Don't think the computers in your pockets, okay? Think computers with half a kilobyte of RAM, okay? So this made it efficient to maybe uppercase or lowercase text, or to compare two text strings case insensitively, because it was just a matter of flipping or toggling a bit. And of course, time progressed and computers started showing up everywhere around the world, okay? And people said, well, we may need something more than ASCII. Guess what? Those computers, most of them, by the late 70s and early 80s, were 8-bit oriented, okay? If everybody thinks that a byte has always been 8 bits, you're mistaken. Don't worry, that's a different talk, okay? Computers used to have 7-bit bytes, 6-bit bytes, 9-bit bytes, but these were 8-bit, which meant that we had all of this range, hey, to play around. What are we going to do with it? And so, the original IBM PC decided to, well, we'll go with this setting because this is nice. We can draw boxes and things. It's nice. And then they decided, well, we forgot about Western Europe because they have these different characters and they need them on their local PCs. Oh, what about the Portuguese? They have different things there. And then the Greek, and then Cyrillic, and then came Windows, and then came Cyrillic for Windows, and so on and so forth. Okay? And all of a sudden, we had tens or hundreds of different ways of encoding text as bytes and bytes as text. Challenge. Of course, many of you may know Randall Munro's webcomics. If you don't, check him out. And this is quite appropriate, okay? And he describes as a situation at some point in time where you have 14 competing standards. And someone comes up and says, we should create something that encompasses all needs of everyone. We create a single unified standard. And then from then on, everybody will use that. And reality is that in a few months, you have 15 competing standards. And that's exactly what happened when the ISO decided to create 8859. You probably heard a lot about 8859, or you crossed your mind with that, also known as Latin 1, Latin 2, Latin things. And they created yet more variations on these encodings, and so on. And what these things had in common is that they were all ASCII compatible on the lower 7 bits, on the lower range from 00 to 7F. And from then on, they weren't. Wow. So people were typing that and getting this. Why? Well, because some computer somewhere got Amélie and assumed, oh, I'll go and encode this according to Latin 1, which resulted in these bytes, because computers know bytes, they don't know texts. And someone else on their own computer or a different piece of software or something picked that up. It was configured in a different kind of setting, and, well, they got this. And of course, the internet only made this worse. You know that already. Enter Unicode. maybe the child of the internet, maybe the solution for all past, present, and future texts, at least until we reach or meet the aliens. We'll see. So in Unicode, a letter or a symbol also maps to a number, but that number is not a byte. It's called a code point. So what's a code point? It's normally represented like this in written or technical specs. So a U, then a plus, and X digits. And if you drill down, this gets you to 1.1 million different code points, okay? So you can now, for the first time, have, say, a single document or a single file that includes Arabic and French and Chinese texts, okay? You couldn't have that before. And even though we have this 1.1 million space for characters or letters or symbols, where are you going? Go there, go there, go there, go there, and we go there. Sorry. Only 15% of that space is assigned, so we have plenty of room to grow, okay? And, oh, it's just moving forward by itself, thank you. Here are a few examples, okay? Code points on the left, the representing symbol, including these friendly guys that we have all been using nowadays, okay? This is written text. So we can think of Unicode, instead of like that kind of table-like thing that I used with ASCII, as a 1.1 million long row of code points matching letters or symbols. Now, Unicode also defines meta information about each code point. There's actually lots of information. In particular, there's a category, so each code point has a category, and say you have two letters, the first, call it the major category and the subcategory, I don't know the technical terms, but notice that these digits are n for numbers, pretty much like this one. This is a fraction, it's also a number, but subcategory here is decimal and here is other, okay? And note these letters, these are letters with the first L, and these are lowercase with the second L, and this is uppercase, and all sorts of variations on the categories. And there's one interesting thing. There's a canonical name for each code point. And the rule is you should be able to specify each code point in written English text ASCII only. These are only letters, okay? So each code point has a canonical name. So Unicode is not only about representation of text, but also about text processing with all of this meta information. So what about bytes? Because computers need bytes. You push something out to the network, you need bytes, okay? And that's where UTF comes in. And the role of UTF, Unicode Transformation Format, is to define how you translate or map or convert these code points into bytes and back. There's UTF-8. Its strikingly important characteristic is the fact that it is ASCII compatible. So if I just have ASCII code points, okay, ASCII compatible texts, I can encode with UTF-8 and produce a file that can be properly and correctly read on a 1970s or 1980s computer. That's useful. Not probably on that direction, but on the reverse, because there's lots of legacy text around the world. So this is an important feature of UTF-8. And there's UTF-16 and UTF-32. The general idea is this, okay? The legacy mechanisms for representing text as bytes tend to match one character to one byte and one byte to one character back. It's a plain mapping. And with Unicode, you have some kind of an indirection. So you have one character to a code point, and then you have one code point can be represented with 1, 2, 3, or 4 bytes. So if you look at a text file, it has 10 bytes. There's no way you can tell it has a 10-letter word or a 3-letter word if I tell you that's a Unicode encoded text file, okay? Forget the assumption that 1 byte is 1 letter. That's no longer true. It hasn't been true for quite a while. Except for those gentlemen that sent that mail to Amelie, okay? They still think 1 character is 1 byte. Now let's take a look at a few encodings of the word resume in possible scenario. So in ASCII, you really can't do that. And code page, blah, 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 from IBM, you could. In Windows, you can. Notice that the bytes are different. All of these are ASCII compatible, so they work. These are code points, so these don't exist as bytes in any computer. These are abstract entities, okay? But then if you go UTF-8, notice that, again, these are ASCII compatible, but these ones, 2 bytes for that letter, okay, in UTF-8. And UTF-16 and UTF-32, and that's okay. So let's move on a bit onto Python and see how these concepts map into Python. And I promise you that towards the end, I'll map these concepts, if I have time, into JavaScript and into Swift a bit. There are variations on the topic, but the fundamentals are essentially the same. So in Python, we have 2 built-in types. One is called str, or string, which supports textual information and should be thought of as a sequence of code points, okay? And then there's bytes, which supports binary information, and you can think of it as a sequence of low integer values, okay? Now, on a REPL, you may represent a Python string between single or double quotes, like that. You get the string back. You can also use this \n curly braces, and between the curly braces, you type that canonical name of the code point, okay? You can use any one you like. This is the exclamation mark. That represents a single code point, and there's your representation of that, okay? So quite expensive, this one, okay? This is just for the sake of demonstration. And you can also type the code points in X, okay, with 2, 4, or 8 digits, and you get this, okay? So 41, this is ASCII compatible, actually, and you get those funny characters, as long as your terminal is properly configured and things. Now, bytes in Python, they kind of look like strings, but they are not at all like strings. You type them like this, possibly, but you add the B prefix, and out comes that. But that's just a representation of bytes, which are numbers. This is a sequence of numbers. But what Python does, for the sake of brevity, is if a given number, say 65, maps to an ASCII character that's visible, then Python will use that ASCII character here. So this is byte 41x and 62 and 63 and 21. Then this is a space, which is byte 20x. And this is byte C9. And Python goes for this canonical representation. But this is not a text string, okay? This is a sequence of bytes where the first byte is 65 in decimal or whatever, 41 in x. That's 65, yes. In particular, when you iterate or build a list over bytes objects, what you get is a list of numbers, okay? If you did that with a string, you'd get a list of each code point in the string individually. So this is a conceptually important concept. Now in Python, we have the ord built-in function, which will give us the code point for a given character, let's say, it's 65, that's decimal, of course, or you can do that for that funky I. This is a capital I with a dot on the top, strange for most of us, but those that know Turkish. Turkish has the dotted / dotless I, so the capital I with the dot is this, and that's 304. I use it here, okay? Remember, if I go x, I should get 130, that's 130x, okay? And I can do the reverse operation, which is take a number, okay, for a code point, give me the string, and I get that again, okay? So strings, textual information, sequence of code points. Bytes are binary information, and going from one to the other, okay, is the process of encoding, and going the other way around is the process of decoding. So even though we don't often do this by hand, we're going to do the encoding and decoding by hand in Python to see what can possibly go wrong and to understand why things go wrong the way they do. Let's define a text string, okay? Hi, pretty simple, pretty inoffensive, ASCII compatible, no problems. And strings have a method called encode that takes an argument. It's the name of an encoding. So please give me the bytes that represent this text string as ASCII. And out comes Python. There you go. There's your B in high, okay? And you ask it for, give me in Latin 1, and you get the same thing. And you ask for UTF-8, and you get the same thing. Guess what? Latin 1, which is actually an alternate name for the ISO 8859-1, UTF-8 and ASCII are all compatible, okay, at the ASCII level, so no surprises here. But if we go UTF-16, then we get something different. Those are bytes. We don't care. We write them to disk. We send them across the network. We do something. That's for computers to deal with, not for us humans. Now, let's raise the bar a bit and use non-ASCII compatible text. There's Amélie. Let's encode it as ASCII. Bang! Unicode encode error. Oh, come on, what's going on? Let's read the message. Can't encode character blah blah in position 2. Position 2. What's in position 2? Oh, that's that funny character. ASCII doesn't know about that one. So what's the X value of that? Yes, that's that E9 that the error message includes. Okay, I got the message. Maybe I need to use a different encoding for such text. So I'll go with Latin 1, and there you go, I got something. Okay? Notice, bytes, ASCII compatible, ASCII compatible. This is not ASCII compatible. This is the byte E9, and then all the others are ASCII compatible. Let's go UTF-8. There you go. AM, okay, ASCII compatible, 2 bytes, C3 and A9, and then Lee. Okay, it's different. So how do we cope with those errors that we got there, okay? When we try to encode Amélie as ASCII, can we cope with that? Well, we certainly can, because the encode method has an optional keyword argument, errors, which defaults to strict, by the way. So this is pretty much the same as before. We'll get the error. We can say, yeah, forget about any errors, okay? Skip. If you don't know how to encode this, just move on, okay? And we get that. Or, well, you know, try to replace errors with something like be creative, and we get that, okay? And that question mark, that's not a question mark. That's the byte value for the question mark in ASCII, because these are bytes. And you can even say, yeah, use an XML character reference, blah, 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 okay? Which may be useful if you're working with XML. Sorry for that. But, you know, ampersand thing, what you call that? Nowadays, you call it probably hash something. But that's XML character replacement for you. Notice that we're losing information here. We're losing information here. However awful this is, you're not losing information, so you just need to handle that. But you have the information. Not bad. Now, let's do it the other way around. Let's pick up on bytes and move on to strings. So I'm going to cheat a bit, and I'm going to create the string. Then I'll create the BL1, which is the Latin 1 encoded bytes for Amélie. And I'll create the BU8, which is the UTF-8 encoded byte for Amélie. And I get this, okay? We've seen these before. And I'll just round trip it, okay? If strings have a encode method, bytes objects have a decode method, which has roughly the same signature, okay? So we go decode my Latin 1 bytes, assuming it's Latin 1, and we get Amélie. And if we do the same for the UTF-8 bytes, it round trips properly. Cool. Now, remember we have these, okay? Now let's decode the Latin 1 bytes as UTF-8, 8859, blah, 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 -5. It's a different codec. There you go. What's that? Okay? That's corruption. No. I'll go decode the UTF-8 bytes with Latin 1. And that's corruption again. It doesn't fail. Keep this in mind. This is the most important thing. It doesn't fail. Why? Because Latin 1 maps all the byte values from 0 to 255 to some characters, okay? So there's no possible sequence of bytes that would fail decoding in Latin 1. Whether that makes sense or not is up to Amélie, but I would say it doesn't, okay? Now, of course, if you decode that sequence as ASCII, it fails because there's a byte with the C3 value, which is clearly above 7F, which fails. Or if I try to decode the Latin 1 bytes as UTF-8, it also fails because UTF-8 has some properties to, you know, not go blindly like Latin 1 to decode things. But this is important. This is interesting. What about how can we handle errors while decoding bytes to strings? Well, we have these gentlemen here. The decode method of bytes objects also includes the optional keyword argument errors, which defaults to strict, so this will fail, we know this. But we can say, as before, as in the encoding process, ignore errors, and we get that, losing information. Or we can decode as ASCII and say replace, okay? And what the decoder does is, for each byte that it can't decode as ASCII, it will populate the string with a funny character like that. It's called the Unicode replacement character, I think. I've seen that in web browsers a lot throughout the late 90s and early 2000s. Maybe you did too. And notice that if we do the same with the Latin 1 bytes, we only get one of those, because the Latin 1 bytes only has one byte for that funny character, and the UTF-8 has two. So we can control some errors, okay? We need to know what we're doing. So while we're encoding, we can get an exception if we're trying to encode something that's not valid somehow, okay? Like an accented character in ASCII. We may lose information if we say disregard errors, but we must do that explicitly, okay? Now decoding is more sensitive, because we will get an exception if something funny comes up, but we may lose information if we override the errors, okay? But we may also lose information when we successfully decode with the wrong codec. And this is the critical path, okay? This is the important thing to keep in mind. You can't just go and decode and hope everything is all right, because it might and it might not. So a few takeaways. If you can decide for yourself, try to encode using a UTF encoder and keep errors at strict. With a UTF encoder, you can encode any possible written text as of today and into the future before we meet the aliens, okay? So it should work and the information will be there. Now, when you decode, if I give you a bunch of bytes, hey, this is the latest works, all the works from Shakespeare, okay? Just decode it. It's a text file. These are bytes. You'll have to guess, or you'll need to ask Tiago, okay, but these are bytes. What's the encoding? Okay? So we really need to know what nature are the bytes we're getting from disk, from the network, whatever, okay? So the outside world, don't think Python, think a running process, any technology, okay? It's just running there. The outside world is files, it's the network, it's maybe your terminal emulator. On Unix it's a file, on Windows it's not. Maybe system calls. Your running program, any running program communicating with the outside world uses bytes. There's no other thing, it's just bytes. You may not be aware of that. Now let's take a look at a few files. Say these two, okay? A book TXT or a client CSV? There's no way you know the text encoding that's being used. You need to ask. Maybe if you're using Python, you'll use a third-party thing like Cardet, which tries to guess, okay, and use some statistical data to say, yeah, there are odds that this is Latin 1, but you really should ask. If you're using, say, YAML or JSON files, the spec says these files must be encoded in a UTF format, so you pretty much have it narrowed down, no problems. And you say if you have XML or HTML, they tend to have embedded information about the encoding. XML has some kind of prefix there, and HTML may have a meta tag, so the technique is you read it as ASCII as far as you can until you find the meta tag, then you rewind and read it properly from there on. Okay, and in Python, if you're reading text files, often, code I see every day, people write open, name of the file, RT. Actually, RT means read in text mode. It's the default, so people don't even type that in. And they omit these two. It works on their computer, yeah, sure. But what's the default encoding that Python will use? Okay, it varies from system to system. So it's good to be explicit. And we can and should use the encoding argument and the errors argument, which behave pretty much like we've seen before. Okay? And the same goes for writing a text file, okay? We should be explicit about which encoding we're using. We're going to produce bytes. Someone will come to us and say, Tiago, what's the encoding on this? I'd better know what I did, okay? So keep this in mind. If you're working with binary files with RB or WB, that's not a problem because you're just working with bytes. Bytes inside your running program, bytes outside world, no problem. Great. So what about the network? If you're using protocols like SMTP or HTTP, okay, these protocols have headers in their communication that specify if the payload is text, they will tell you which character set or encoding is being used for the payload. Good. If you're using SSH, well, SSH is a binary clean protocol. It's up to the software on both ends to decide whether they're transferring text or other types of things. So SSH is bytes clean, you don't care. If you're using any other protocol, well, check the RFC, check the spec, okay? If it's moving text around, there should be a spec, and you should follow it. There's a node protocol. I don't think it's being used nowadays as it used to be in the late 90s, but IRC has a serious problem with multi-encoding things because it's kind of byte transparent. It's up to each client to define that, so people tend to get funky things. So let's recap, okay? You have strings, you have bytes, you encode and decode. All of this can fail. You may lose information. You need to know what you're doing. All of this is often handled by libraries, okay? So keep this in mind. Advice? Well, if you're getting bytes from somewhere, and that's supposed to be text, decode them as soon as you get them. Then process and or store with string objects, okay? If it's textual data, process with the proper tools. In Python, those would be string objects. And then when you're out to push them somewhere, okay, encode it as late as possible. Maybe if you're using some kind of backend service, a database or a Redis thing or a queuing system, the libraries or adapters will take care of that for you, or maybe not, okay? Just know that when it goes out, it will go out as bytes. Again, if given the choice, encode in UTF. If you're given bytes, you'll need to know, okay? Otherwise, if you guess, you're taking chances, you may be corrupting data. Oh, by the way, avoid errors different than strings. I think this is a good general advice, unless you really know what you're doing. Because we are humans and computers exist to serve us, so they should do what we say, okay? And we should take responsibility on that. A few more funny things, okay? Because language is complex, written text is complex, and thus Unicode is necessarily complex, okay? I would love to say, oh, this is it. If you go out to the world, this will all work fine. It will not, okay? So most of us looking at that would say, oh, that's a C, the C letter. I learned that when I was 5 or 6 in school, right? No, it's not. It's a Cyrillic capital letter S, I don't know. Anyone know Cyrillic, the name of that? And the code point is this. Oh, by the way, that's a Roman numeral, okay? There's a code point for that in Unicode, remember? Is that silly? Is that not? I don't know. But certainly, this one has a category of L. This is a letter. And in Unicode, this one has a category of N. This is a number. Oh, by the way, you have another one, and that's the Greek capital letter Ba, okay? And it's a different code point. They all look the same. And there's still the capital letter, Latin C. It still looks the same. In Python, you'd get something like this. Notice that on this terminal emulation font, the first C is kind of different, but you can be fooled. So if you compare them, yeah, they're all different, okay? Does it make sense? It does, okay? These things are called Unicode confusables and are things, let's call them letters, that look the same, but they are semantically and conceptually different. Some people may be particularly interested in this. This feature, let's call it of Unicode, is the basis for lots of phishing that's being done every day around the world, okay? You get an email or a website or something. Regarding domain names, there are specific RFCs to handle this. I won't get into that. There's IDNA. If you want to know more, come talk to me after this. It's important if you're handling internationalized domain names. But this is just a reality. There are lots of different, conceptually different things, okay, characters, code points, that look the same. What about these? Well, these certainly look the same, and they are the same, okay? But this one is the Latin capital letter E with a Q, and the code point is C9. Whereas that one on the bottom, 2 code points. Not 1 code point, 2 code points. How many symbols or letters? 1, okay? This is important. This is the Latin capital letter E, plain old ASCII-like friendly E. And this code point is a combining acute accent. Wow. You can do that? Yes, you can. And the teletypes also could. Okay, you typed an E, moved the carriage back, and printed an accent. Computers are only doing this now, okay? So there's some room to catch up. Here's the Python equivalent of this. So that's C9, A, and B is the 45 and 301. So A and B look exactly the same, but the length of this string is 1, and the length of this string is 2, because in Python, the length of a string is the number of code points, not the number of visible characters, whatever that means, okay? It's just the number of code points. Are they equal? No. So what? What do I do? Because they are semantically equal, okay? They mean exactly the same thing. So let's take a quick detour. And in Python, in the standard library, there's the Unicode data module, which we can import and use the name function there. That will give us the canonical name for a given code point. Okay, useful. And you can do that one, and that's the thinking phase. And how can we use this? Well, let's use it like this. Let's define a function, we don't worry. We just give it a string, and it prints out the names of its Unicode code points. So we do that with the A as expected. It's a single code point, that's a thing. And we do that with the B, you get 2 code points, okay, 1 per line, those are the names. Now the fundamental Unicode concept is this: normalization forms. Unicode establishes that some characters, for lack of a better name, or without going into much technical details, can be represented either in a composed form, in a single combined code point, as that E there, or that Korean letter there, or in their decomposed forms, this way, on the right-hand side, okay? And they're both equally valid, and either form represents the same conceptual thing, okay? That's an E with an accent, or this Korean letter, okay? Now, we can, in Python, fix this. Remember, these are different, but we can use the normalize function in the Unicode data library to say, give me A in what's called the blah, blah, blah. Okay, this is the composed form. Normalized, blah, 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 form composed. So give me A composed. And by the way, do the same as B, okay? Pick up whatever B and normalize it to the composed form, so I get A under NFC and B under NFC, and now these are true. Now I can compare them, okay? And if I look at the Unicode names in B, I know I had 2, but in B and FC, I have a single code point. It's been combined. Scary stories, okay? Scary story number 1. This is international text. And I can do uppercase on that, uppercase on German. We've seen it works, and I can do it in Turkish, okay? Great. Now let's round trip it and do upper and lower case, okay? French, you get Amélie, okay, it's a proper name, should probably be capitalized, but it's still Amélie. Conceptually, it's the same for a human being, great. You can do the German Strasse thing, you get Strasse like that, it's still valid German, it represents the same concept. Let's do that with the Turkish word, and you get a different thing. Dotless eyes, dotted eyes, okay? Well, these words have a different meaning, and there's a horror story somewhere on the internet. I linked to it on Wikipedia, so it's probably serious and not like just movie. People got killed because some mobile phone software or telco software messaging around, okay? One of these got translated into the other one. People got angry, picked up guns, killed people, okay? It's always bad picking up guns and killing people, but you don't want to, to be like, oh, I did the uppercasing wrong. You don't want to be there. A different scary story. This is, and I also linked to this story in detail on my talk notes, how you could hack a Spotify account, okay? So you created a username with funky code points. Turns out it looked like bird. And don't ask me why there are several different capital B's on code points, but those are capital B's, but not the common normalized plain ASCII code points, which are kind of different, even visually, okay? And you use the Spotify API, which is not this is clearly pseudocode, to create a new account with that funky username and your account thief email. And you could do this because Spotify was pretty proud. We're very inclusive, and you can have any username you like with any code point. You want your username to be smileys and the funky thing, that's okay with us. So, you know, music, it's nice. So they allowed you to create a new account with this. And then they had a different API where you asked, I want to reset the password for this account, and here's the email, by the way. And you would allow, it would allow you to reset the password, but not for your funky bird account, but for the plain old original ASCII-like bird account. So guess what happens, yeah? I got that, now I can log in as the bird's attacked account with the credentials I have, and I'm using the thief's target account. Well, Spotify had serious problems on these two APIs because they didn't properly normalize, okay? Normalizing is important. So key takeaways. Text processing is non-trivial. It's really non-trivial when you think of it and if you want to take care. There are, unfortunately, lots of pitfalls with Unicode, but that's life. Language is complicated, text is complicated. There's no way around confusables. You need to know. One code point is not one character, okay? You can have 3 code points, and that's the same character, an E with an X and something. And remember, by the way, 1 code point is not 1 byte. So you can have like a 10-byte thing, which is a single visible letter on your screen or on your printer. If you must compare strings, and sorting strings means comparing, okay? You're comparing strings. Especially if you're getting strings from somewhere you don't know, maybe from a web browser, from a database. Are you going to compare them? Sure. Normalize them. If you take a single thing from here is normalize your strings, okay, to some common thing, composed, decomposed, whatever, but you normalize them to the same format and then compare. And changing case, by the way, is language dependent, okay? Who could have told that? And since I promised not to be strictly about Python, I'm really on time, okay? JavaScript, these things are simpler in JavaScript for you JavaScripters in the audience, okay? Here are 2 strings, okay? The same resume. They have different lengths, pretty much as in Python. You compare them, they're false, okay? But in JavaScript, normalizing is simple. There's a normalize method on strings. You normalize it, say, to NFC, and now they're true, okay? Simple. And next, in case conversion, okay, there's the Turkish word. If you do to upper and to lower, you get the dots, you have the problem, people get killed, awful. We don't want that. So there's the to locale uppercase, blah, blah, blah. You pass it in the locale. You do the to locale uppercase, to locale lowercase, and life is beautiful, okay? So you need to know the locale, again. And if you want to see Swift, it goes pretty much the same way. The syntax is different, but you know, the concepts are the same. You go a count, tells you you have 6. 6 what? In Swift, strings don't count code points. They're more sophisticated because b count is also 6, even though we have more, okay? So in Swift, strings are equal. It comes for free, okay? You don't have the problem of normalization. But you do have the problem of code conversion, okay? And if you upper and lowercase, you have a problem there, okay? But if you use a locale and do tricks and things, you can do the uppercase with the locale, and you get it right if you lowercase back with locale, okay? So parting thoughts, different languages, different tools. Modern ones handle Unicode just fine, but you need to understand the fundamentals. You need to know your tools and build from that. There are no silver bullets. Thank you very much, okay?